Hello students, welcome you all. In my today's lecture, I will discuss the correlation diagram for allylic systems. In my previous lectures, I told you about the correlation diagram for 4n electron system and for 4n plus 2 electron systems. Okay, now this allylic systems, they can also be 4n electron system or 4n plus 2 electron system. Like this allylic cation, it is 4n plus 2 electron system, and allylic anion is 4n electron system. So we are analyzing actually the electrocyclic reactions with the help of orbital symmetry correlation method, that is with the help of correlation diagram. In orbital symmetry correlation method, we draw the correlation diagram to analyze the electrocyclic reactions. Okay, so what was the selection rule for the electrocyclic reaction which we have to analyze? So this is the selection rule for electrocyclic reaction. So we usually study two type of reactions in pericyclic chemistry: 4n plus 2 electron systems and 4n electron system. So two type of system we are going to study in pericyclic reaction. So 4n electron system under thermal condition, the 4n electron system show cone rotatory motion of the orbitals, whereas under photochemical systems, the 4n electron systems, they show disrotatory motion of the orbital. In the same way, for 4n plus 2 electron system, they under thermal condition, they show disrotatory motion of the orbital, and under photochemical condition, they show cone rotatory motion of the orbital. So this is the selection rule that we are analyzing with the help of orbital symmetry correlation method, that is by drawing the correlation diagram. So let's see how we can draw the correlation diagram for allylic system. And allylic system, it may be 4n electron system or the 4n plus 2 electron system. So if we have allylic cation, then it is 4n plus 2 electron system because it has 2 electrons. If we have allylic anion, it will be 4n electron system because it has 4n electrons. So suppose I take the allylic anion. Suppose this is our allylic anion. Okay, so this allylic anion, so if we want to draw the this correlation diagram, suppose I draw, this is cyclopropenyl cation, and this cyclopropenyl cation in presence of either heat and light, so this will open, and it will form the allylic cation. So this allylic cation is formed. So in this reaction, this reaction can occur either in presence of heat or it may occur in presence of light. And this opening of this, the ring opening reaction is taking place here. So ring opening reaction, either it may occur by the cone rotation of the orbitals or by the disrotation of the orbital. Okay, so in this cyclopropenyl cation, so if you will see the orbitals involved, what are the molecular orbitals involved in this reaction? So here the molecular orbital involved are, this is the sigma, okay, sigma. So corresponding to this sigma bond, the molecular orbital will be, this sigma bond is involved in the reaction. So corresponding to this sigma bond, the molecular orbital involved will be sigma and sigma star. And one of this p orbital is also present. One of the p orbital is also present for this carbocation. So p orbital is also involved. In the same way, if you will see the molecular orbital for this allylic cation, then I have already discussed the this molecular orbital diagram for the allylic systems. So in which it will have 3 molecular orbital, and that can be designated as suppose psi1, psi2 and psi3. So these are the three molecular orbitals for the allylic cation. And the same way the allylic anion will also have the three molecular orbitals. Okay, so one is bonding, this is non-bonding, this is anti-bonding, or I can write it for x by psi3 star, I can also write psi3 star. Okay, now let's see the correlation diagram. So this is converting into this. Here ring opening reaction is taking place. So for this cyclopropanol, this cation, so three molecular orbitals. One is sigma star. Suppose this is sigma star. Sorry, sigma. Well, suppose this is sigma. Okay, sigma being the strongest bond, so that would be the most stable. Okay, then sigma star at the highest energy, we will have the sigma star, and the non-bonding orbital, this would be the, suppose this is a p orbital. Okay, now so these are the three molecular orbital for this one, and in the same way this is now converted into allylic cation, and this allylic cation is having the three molecular orbital. One is psi1, psi2 and psi3 star. So this psi1 I am writing over here psi1. This is psi1. Okay, this is our psi3 star, and this is the psi2. Okay. Now suppose first I will discuss for the disrotatory motion of the orbital. Suppose disrotatory motion of the orbital. Okay, so we have to see whether when disrotation of the orbital, whether it is allowed under thermal condition or photochemical condition. So this is how many electron system this is? This is as 2 electrons are involved over here. So that's why this is an example of 4n plus 2 electron system. This is an example of 4n plus 2 electron system, whereas here this n, this is equal to 0 because 2 electrons are involved, or this is a 2 electron system that we can say. Now what you will see in this case, we have to see that for disrotation, what I have told you, for disrotation, sigma mirror plane symmetry is maintained. So sigma is maintained, or we can say mirror plane symmetry is maintained in reactant and product. So one of the feature of pericyclic reaction is that the reactant orbital and the product orbital should have the same symmetry, is having the same symmetry. So in reactant and in product, what is maintained during disrotation? Sigma is maintained. So here during disrotation, the sigma is maintained. Sigma is maintained in reactant as well as in product. So let's see whether these molecular orbitals are symmetric with respect to sigma or not. These molecular orbitals are symmetric with respect to sigma or not, that we have to see. So if you will see this sigma bond, this is our sigma bond, this is our sigma, so plus plus minus minus. So if you will see, when we pass a mirror sigma plane or mirror plane, and in front of plus we have plus, in front of minus we have minus, that's why this is symmetric with respect to sigma. So this sigma molecular orbital is symmetric with respect to this mirror plane. Now what about this p orbital? Now what about this sigma star? So this is our sigma star. Here it should have minus, this should be plus. So in this case, you will see in the front of plus we have minus. In a mirror, in the front of plus, this is minus, that's why it is anti-symmetric. This is not symmetric. So you can write it is anti-symmetric with respect to the sigma. What about p? So this is the p orbital. This is p orbital plus minus. One lobe has having plus sign, another lobe having minus sign. So if we pass a mirror plane, if we pass a mirror frame from the center, then it is symmetric. This is symmetric with respect to sigma. So I should write sigma S over here. Now what about this sigma psi1, psi2, psi3 of this allylic cation? So all of you know this allylic cation, 3 molecular orbitals are there. Okay, this is psi1, all having plus sign. This is psi1 and psi2. Psi2 is the non-bonding one. So for non-bonding, the one of the node that will pass through the carbon atom. So this is through the carbon atom, and this will have a plus sign. This is minus, this is minus, this is plus. And third is psi3 star. Psi3 star, all will have alternate sign, plus, minus, plus, and minus, plus, minus. So we can see, you can see the molecular orbital diagram. In my previous lecture, I have discussed the molecular orbital diagram for this odd carbon system, 3 carbon system, 5 carbon system, as well as the 7 carbon system. In this way, we can draw the molecular orbital diagram for any type of odd carbon system. So I have given that rule there. Okay. So if you will see here, if mirror plane is passed over here, then no doubt this is in front of plus, we have plus, in front of minus, we have minus. That's why it is symmetric with respect to the sigma psi1. What about psi2? If you will pass mirror plane, in front of plus we have minus. That's why it is anti-symmetric with respect to the sigma. It is anti-symmetric. What about this psi3? If you will pass the mirror plane, then this is symmetric with respect to the sigma. This is symmetric with respect to the sigma. So that's why. So in this way we have seen the symmetry of this mirror plane for reactant and product. Now in correlation diagram, what we do? Symmetric orbital is correlated with the symmetric molecular orbital. Symmetric molecular orbital is correlated with the symmetric molecular orbital, and anti-symmetric is correlated with the anti-symmetric. So the sigma, which is symmetric with respect to the mirror plane, that should be correlated with the symmetric orbital. So this is symmetric as well as this is symmetric, but this is having the lower energy. That's why it is energetically it is favorable. Now if you will see this one should be, this P is symmetric with respect to the sigma. So this should be correlated with the symmetric molecular orbital. So this psi3 is here symmetric. That's why I will correlate it with this one. And this is anti-symmetric. This is anti-symmetric. That's why I will correlate like this. Okay. So this is the correlation, simple correlation diagram for this allylic system. Now let's see whether this disrotation of this orbital is allowed under thermal condition or under photochemical condition. So this allylic cation, this is our 4n plus 2 electron system. So this when disrotation of orbital occurs, then when it will take place under thermal condition. So let's see whether we are able to prove this one or not with the help of this correlation diagram or not. So let's see it. So here it is 2 electron system. That's why I should fill 2 electron over here. And now in sigma we have 2 electrons. Okay, and these 2 electrons are going into the psi1. These 2 electrons are going into psi1 under thermal condition. So let's see first under thermal condition. In thermal condition, these 2 electrons will remain in a ground state. Under photochemical condition, one of the electron will go into the excited state. So this is the case here. 2 electrons are going into psi1. This is ground state. This is also ground state. So this is energetically, this is allowed. So this is the allowed condition. So which you can also see in this selection rule. So under thermal condition, disrotation of molecular orbital takes place. But it will not be the case for the photochemical condition. So let's check it. Under photochemical condition, so one of the electron will get excited to this one, p orbital. So now let's see, sigma having the 1 electron, p is having 1 electron. Now sigma electron is going into psi 1 and p electron, this p electron is going into psi 3 star. Psi 3 star. Okay, psi 3 star. So this is higher energy excited state. This is excited state. This is higher energy excited state. So this is our excited state and this is higher energy excited state. Okay. So this is energetically not favorable. So that's why we can say this is not favorable. So under this rotation, what we have seen under this rotation, this can only take place. This rotation is undergoing take place only in thermal conditions. So this we have proved. Okay. In the same way, when the conrotation of orbital occur, it occurs only under the photochemical conditions. So let's see for photochemical condition. Okay. So we will now check for con rotation. So second, con rotation. So what will be the diagram for this con rotation? So this diagram will get changed for con rotation. Okay, so for con rotation, all of you know, for con rotation, which symmetry is maintained during the con rotation? We know that C2 is maintained during the con rotation. So for con rotation, C2 is maintained. So here the con rotation. So in reactant and product orbital, C2 should be maintained. So if you will see the reactant molecular orbital, whether this is symmetric with respect to C2 or not. Sigma is whether symmetric with respect to C2 or not. This is sigma. This is our sigma. And if we draw one of the rotation axis and if we rotate it by 180 degree, then after rotating it by 180 degree, then in place of plus, plus will come, and in place of minus, minus will come. It means we are getting the, after rotation, we are getting the same molecular orbital. That's why it is symmetric with respect to C. What about this P? What about sigma star? So sigma, this is our sigma star, plus minus. Now if you will rotate it by 180 degree, what will happen? In place of plus, this minus will come. And in place of this minus, this plus will come after rotating by 180 degree. So that's why it is, we are not getting the same molecular orbital. That's why it is anti-symmetric with respect to C2. Now what about this P? So this is the P orbital, this is P orbital plus and minus. This is P orbital, and suppose if you draw the this axis and if you will rotate by 180 degree, then at the place of plus this minus will come. After rotating by 180 degree, then at the place of this plus, minus will come. This minus will come, that's why it is anti-symmetric with respect to P. And what about this? After, if you will rotate it by 180 degree, then whether this is symmetric? No. So at the place of plus, this minus will come. At the place of plus, this minus will come. So C2 is anti-symmetric. In the same way, this C2, psi 2 is symmetric, and psi 3 star is anti-symmetric with respect to. Okay, so let's correlate the orbitals having the same symmetry. So this symmetric is correlated with this symmetric. Okay, this symmetric is correlated with this symmetric, and this anti-symmetric is correlated with this anti-symmetric. This anti-symmetric, that should be correlated with this anti-symmetric orbital. So in this way, like this, this is the correlation diagram for the this one for con rotation, when these orbitals are undergoing con rotation. Now let's see. Let's check this selection rule. So first of all, under thermal condition. whether under thermal condition Kohn rotation takes place or not. Let's check. So we have under thermal condition both the electrons that should be present in a here, that should be present here. So if this is present over here, this is present over here, then what you can see that this two electrons are present in sigma, and these two electrons are going into side 2. These two electrons are going into side 2. Okay, so if you will see, then this is ground state and this is the first excited state. This is first excited state. So this is not allowed. And under photochemical condition, if you will check, so this is not allowed. Okay. Now under photochemical condition, what you can see here, this is our one electron that will get excited over here. Sigma is having one electron, P is having one electron. So this sigma electron is going into side 2 and sigma electron is going into side 2, P electron is going into side 1. So this is our first excited state and this is also first excited state. This is allowed. So this is allowed. So we can check here for Kohn rotation, when the Kohn rotation is only allowed under photochemical condition and it is not allowed under the thermal condition. Like this we can check it. So for allylic anion, this diagram will remain same, and if we are taking the allylic anion, then number of electrons that we will fill here, that would be 4 electrons would be there for the allylic anion, and we can check that whether that would be allowed or not. So for allylic anion, if you see, okay, so for allylic anion, this is our allylic anion and here we will have negative sign. So in this case, for allylic anion, okay, so this will go over here and this will go over, sorry, so this will come over here, this will go like this. So this would be the allylic anion, and here the number of electrons involved is 4. Number of electron involved is 4, and if we will check this one, then we should see, and we can see this would be now 4n electron system. This will be 4n electron system. Okay, this is 4n electron system. Here it means n is equal to 1 over here. Okay, so now in this case if you will see, then number of electrons involved is 4. Number of electron involved is 4. Okay, now if you will see under thermal condition, and when Kohn rotation take place, then what you will see under Kohn rotation, sigma is having 2 electron, P is having 2 electron, and this sigma electron is going into side 2. Okay, and this P electrons are going into side 1. Okay. Sigma electron is going into side 2 and P electron are going into side 1. So like this. So here in this case, if you will see, then this is our first excited state and this is also first excited state. This is first excited state and this is first excited state. So under thermal condition, as you can see, this is for 4n electron system, the Kohn rotation takes place under the thermal condition. And if you will see under photochemical condition, if you will check under the photochemical condition, Now one of the electron from side p orbital, that will go here. One of the electron is going over here. So if you will see, then this is side 2, p is having 1 electron, sigma star is having 1 electron. So this sigma electron is going into side 2. Okay, sigma electron is going into side 2, whereas p electron is going into psi 1, and this sigma star electron is going into psi 3 star. So this is first excited state, this is higher energy excited state, this is higher energy excited state, and this is our first excited state. So this is not possible. Okay, in the same way we can see for this rotation also. So if you will check for this rotation, so what was the diagram for this rotation? So if you will see for this rotation, so diagram for this rotation, it was, suppose I write here this rotation where sigma is maintained for this rotation. Okay, and the diagram for this rotation was this was the diagram for this rotation. Okay, so this was the diagram for this rotation. Okay, now so under thermal condition, so here mirror plane symmetry is maintained. So what we will see the mirror plane symmetry in reactant orbital and product orbital. So here this is symmetric with respect to mirror plane, this is anti-symmetric with respect to mirror plane, and this is symmetric with respect to mirror plane. This psi 1, this is symmetric with respect to mirror plane, this is anti-symmetric with respect to mirror plane, and this is again symmetric with respect to mirror plane. So symmetric is correlated with symmetric, this symmetric is correlated with symmetric, anti-symmetric is correlated with anti-symmetric. So under this rotation, 4 electrons are present in allylic anion system or this 4n electron system. So 2 electron over here, p is having 2 electron, and this 2 electron is going into psi 1, this p electron is going into psi 3 star, okay. So this is the higher energy excited state, and this is first excited state. So this is not possible. So energetically this is disfavored. So this is disfavored. Okay. Now if you will check under, this is under a thermal condition. This is under thermal condition. Now we can check for the photochemical condition. Okay, under photochemical condition, if you will see, then sigma, this electron will go get excited to here, and sigma is having 2 electron, p molecular orbital is having 1 electron, sigma star molecular orbital is having 1 electron. Okay, now sigma is going into psi 1, p is going into psi 3 star, and sigma electron is going into psi 1. So this is our higher energy excited state, and this is higher energy excited state. So this is feasible, this would be favored. So what we can see under this rotation for 4n electron system, under when the disrotation of orbital takes place, this will take place under photochemical, and this will for this one, this will take place under photochemical condition. This is so in this way we can analyze the electrocyclic reaction with the help of a correlation diagram. Now in my next lecture I will discuss the analysis of this selection rule for this electrocyclic reaction with the help of frontier molecular orbital method. Thank you.